Okay, so last episode we were talking about, I guess, the connection between solving linear systems and the image of a linear transformation. So I just wanted to tie in, again, if we have the same sort of system of linear equations, so maybe I'll copy this guy. Let's copy this. Okay. So we do the same type of thing that we did before. Uh, but this time, let's look and see what happens if you don't let each of these be a set of arbitrary constants, but you make all of these guys equal to 0. Okay? Then as we know, when that situation happens, your system of equations is no longer just a regular system. We call it a homogeneous system. Okay? And what's happening here is you have your Rn, that's your domain. You have your Rm, that's your codomain. You take the 0 vector from your codomain, which we'll call the 0 vector with a subscript of m here. And what are the solutions to this system? So the solutions to this system come from somewhere in Rn. So we could put a little circle over here. These are all the solutions. These are all the values of x that get mapped to the 0 vector, right? So this little space here, this collection of vectors that gets mapped to 0, right? So this is the collection of vectors mapped to 0. When it comes to a matrix, we call this the null space of the matrix, right? And if you were to look at the same situation, but this time, instead of thinking of it as a system of linear equations, if you were to just take that same picture, oops, copy it. So you would take the same exact picture, but instead of thinking of it as a solutions to a system of equations, you think of this as like a linear transformation, then the same object right here, this object turns out to be what we call the kernel. So this is the kernel of T, right? So the kernel of T is really the same thing as the null space of T. The kernel of T, this is for linear transformations point of view. And the null space of T is just the matrix point of view. So a matrix subspace. All right. So I had kind of wanted to mention this previous episode, but the video was getting long, so I just stopped it. Okay. So let's change gears for a second. Let's say that you wanted to talk about vector spaces. Okay. Now, vector spaces, you have these 10 axioms, right? And the classic example for you guys, sort of the motivating example, will be Euclidean space, Rn. We call this Euclidean space, right? And so I want you to pretend that you have this Euclidean space. Let's just pretend, for example, that you're looking at R2. Okay. Now you have a basis for R2. And as we know, a basis has two properties. One, it has to be linearly independent. So this is a set of vectors. Call it B. This is a set of vectors. In the case of R2, it only have two vectors. We'll call it B1 and B2, like this, right? And what do you know? You know that they have to be linearly independent and you know that the span of these two basis vectors should equal to all of R2. So when these two conditions happen, then you know you have a basis. Now, what's so great about this? I mean, there's many things great, but is there a main takeaway? So the main takeaway, I would say, is that every point in R2 uh, can be expressed uniquely um, as a set of coordinates. Okay. What do I mean by that? I mean, you have R2 over here, right? And you should think of this as two-dimensional space. So, in two-dimensional space, you have some point over here, x, y, right? But we can also think of the coordinate point of view, the coordinate world. And in the coordinate world, this is just a space of ordered tuples. So we call these ordered two tuples. And what's happened is throughout your life, you've been using these two things you've been using these two things to mean the same exact thing. In other words, I say a pair of coordinates, and you automatically picture a point in space. Um, and this happens very naturally to you. So what I want you to imagine is, the world that you've been looking at has always been in terms of what we call the standard basis. So the standard basis is this E1 vector and E2 vector like this, right? And E1 is the vector 1, 0, and E2 is the vector 0, 1. So when I say the point x, y, you guys know that that means go in the x direction by x amount and go vertically in the y direction by y amount, right? So what happens if I have a new basis? So in this case, my basis B was 1, 0, and 0, 1, right? So let me write that somewhere. Let's say B here is, 1, 0, 0, 1. I hope it doesn't bother you. I switch from rows to columns and columns to rows all the time. Okay. But let's say instead you looked at a different basis for R2. Let's say for your basis, let's this time call your basis B to be, we'll have 1, 0, but we'll also have 1, 1. Okay. So when you look at this situation, what happens? Well, in this situation, your 1, 0 looks something like this, but your 1, 1 actually looks something like this, right? So let's pretend that I were to, let's pretend that I was to express the vector. Let's say you have a vector over here, V. Let's say that V is equal to 2, 2. Okay. So if V is equal to 2, 2, we know where that point V for V looks like. So that point looks something like around here. I'd say this is 2 and this is 2. So 2, 2 is this point right here, right? Now, if you were to think of the coordinate point of view, um, in the coordinate point of view, this vector is not going to be expressed with the coordinates 2, 2. The reason why is 2, 2 would be the coordinates with respect to the standard basis. But if you're talking about with respect to this new basis, the new basis B, maybe I should call it B prime so you don't get confused. What does that coordinate mean? A coordinate would mean you have A times the first basis vector, which is 1, 0, plus B times the second basis vector, which is 1, 1. And you're hoping to attain that 1, 1 vector, that 2, 2 vector that I had mentioned. Okay. So I think if you look at this situation, I hope it's pretty obvious to you guys that when you let A be equal to 0, and you let B be equal to 2, then this, and you add that result together, that's how I'm going to get the vector 2, 2, right? So in this case, the coordinates with respect to, so you put WRT to stand for with respect to B prime, this is going to be equal to uh, 0, 2, right? And why is that 0, 2? It's equal to 0, 2 because the first coordinate of the ordered basis is going to be 0, and the second coordinate of the ordered basis has to be 2. So we simply list the coordinates there. So how is someone supposed to know whether I'm referring to the coordinates with respect to the basis B or the coordinates with respect to the basis B prime? Well, what we do is we say, there's a couple ways we could do it. One way that we do it is we sometimes write the standard basis. So you write the thing with the standard basis, which would be like 2, 2, but then you put a little sub B prime here to indicate that you want to take the coordinate vector of that. That's somewhat common. The way that our book does it is instead of doing it that way, it writes it like this. So let's erase this. It actually calls the coordinate, it gives the coordinate function a name, so it calls it CB prime. This tells you, oh, we're spitting out the coordinates with respect to B prime. And then what are you spitting out the coordinates of? You're spitting out the coordinates of the vector 2, 2. So we have this, okay? So what this kind of means is that when you look at your standard basis, if you look at the grid of the standard basis, it's sort of like, oh, you can extend the first basis vector a certain amount, and you get these um, vertical lines. You can extend the second basis vector by a fixed amount, and you get these lines like this. So it looks like you have a perfectly square grid, right? If you were to look at what sort of the graph paper for B prime would look like, uh, you still have a whole bunch of horizontal lines that run parallel to the first basis vector, right? So you'd have like 1, 2, 3, 4, like this. But then the other axis would be at a 45-degree angle. So that's going to kind of look more like this. 1, 2, 3. So your graph paper in this, with respect to B prime, it looks kind of more like parallelograms than a square grid, right? So, so we have this power to change the basis to describe, so the point of this is that having different powers or having different coordinates, basis vectors, sorry, basis vectors gives us different ways to, I'm going to underline this word, uniquely write vectors in R2. Or let me say it, let me actually retract here. Uniquely write, I'm going to put all vectors in R2 in terms of different bases. Okay. So this uniquely part, this part comes from the linearly independence. And the all part, that part comes from the fact that the basis spans. Right. So since we know that the basis spans all of R2, we can write every vector as a linear combination of vectors from our basis. And since we know that we have linear independence, that will enable us to write these vectors uniquely. Okay. So this is probably a good place to stop, and I'll pick this up later elsewhere.